everybody, it's Mrs. Pound, and I'm back with Chapter 3 from Conceptual Physics. It's about projectile motion. So we were talking about linear motion, motion in just one direction. Projectile motion involves motion in two different directions, up and down and side to side. So our objectives today are to distinguish between a vector quantity and a scalar quantity and give examples of each. We're also going to draw vector diagrams for velocities and use the parallelogram method to find the resultant of two vectors that have different directions. Also, given a vector, we're going to resolve it into horizontal and vertical components. That sounds like a lot, so let's get started. So the first thing we're going to take a look at is section 3.1, vector and scalar quantities. What does that mean? We've already kind of talked about this in class. Remember, a vector quantity is a quantity that has both magnitude and direction. Some examples are velocity and acceleration that we have already talked about, and another example that we're going to talk about in the future is force. A scalar quantity is a quantity described by magnitude only, so it's a number only. Examples are mass, volume, and time. So the first thing we're going to take a look at in section 3.2 are velocity vectors. When velocity is represented as a vector, the length of the arrow represents the speed, the length of the arrow is drawn to a suitable scale, and the direction of the arrow shows the direction of the motion. So I'm going to show you an example. An example is draw a vector to represent 60 kilometers per hour to the right. So I'm going to switch over to some graph paper and show you on this on graph paper. Okay, so when I am drawing vectors on my graph paper, I have to tell what the scale is. These squares on this graph paper all are 1 centimeter. So for all of my problems, I'm going to say that 1 centimeter equals 20 kilometers per hour. So if I want to represent a 60 kilometer per hour vector to the right, I have to draw a dot here. If it's 60, that'll be 3 boxes. And I draw an arrow to the right to show the direction. So this arrow represents a 60 kilometer per hour vector to the right. Once we know how to draw just one vector, we can look at a problem with multiple vectors in it. For example, an airplane travels at 80 kilometers per hour. What is its velocity relative to the ground if it is flying with a 20 kilometer per hour wind? I'll switch over to my graph paper to show you how to do this. Okay, so I am just going to continue with my other problems on this same graph paper. And this time my problem involves an airplane traveling at 80 kilometers per hour. So I'm going to draw this going up. We're going to say that it's going north. So here is my 80 kilometer per hour airplane. I need 4 boxes. And I'm going to draw it going up. We're going to say that that's north. So 80 kilometers per hour. That is the direction. And it is flying with a 20 kilometer per hour wind. So that would be 1 box. I'm going to draw that in. Arrow up because it's flying with it. And this is 20 kilometers per hour. So what I can do is, if this is with the wind, I can add these. The plane actually gets a boost with the wind, and maybe you know this from experience. So I add these, and relative to the ground, the plane is actually flying with a velocity of 100 kilometers per hour. And we can see this from our example. We can experience this on a plane. If the plane is flying with the wind, it will take it less time to travel because it's traveling faster. As we saw from our problem, an airplane flying with the wind gains speed. Here's another problem. What if, instead of flying with the wind, the airplane is going against a 20 km/h wind instead? Let's switch over to our graph paper to take a look at that problem. Now our next problem is, what if this same plane is flying against the wind? What will its velocity be relative to the ground? Well, let's draw in that same 80 km/h vector. So this is 80 km/h. But this time, there is a 20 km/h vector going against it. So this is against the wind. In this case, we have to subtract. And what we end up with when we subtract 20 from 80, we get 60. So we have to redraw that, and we have a 60 km/h vector. The plane is not going as fast, and we can also see this happen in real life. It appears as if the plane is going slower. As we can see from the problem that we worked out on the graph paper, an airplane flying against the wind loses speed. Another problem is, well, what if it's not flying with or against the wind, but it's at right angles? So we have the same 80 km/h airplane flying north is caught by a strong crosswind of 60 km/h blowing from west to east. What is its velocity relative to the ground? Well, let's switch over to our graph paper and take a look at the problem. Now, our third problem with this plane is, what if we have our 80 km/h airplane flying north, but it's caught by a 60 km/h crosswind blowing from west to east? What is its velocity? So we'll draw in the 80 again. One more square. So this is 80 km/h. But this time there is a wind blowing this way, 60. So we have another vector going this way at 60 km/h. This is a lot like if you've ever swam in a stream and tried to go straight across. You don't go straight across, do you? You actually go diagonally. And so that's what happens in this case. And so I'm going to show this with the parallelogram method. What we do is we box this in. Here our parallelogram is a rectangle. And then we draw what we call the resultant diagonally to the other corner here. This is the parallelogram method. Then what we can do is we can measure the resultant, and I get 5 centimeters, but remember, each centimeter is 20 km/h, so 5 times 20 gives us a resultant of 100 km/h. Relative to the ground, the airplane is flying at 100 km/h, so it is actually flying a little bit, it appears to be flying faster than it really is. Well, the wind gives it a boost, right? Okay, just like if you were swimming in a stream, you would be taken down stream by the stream. You would be going faster than you were swimming just on your own. It's the same idea with this airplane. It's traveling in more of a diagonal and it's going faster. Gets a boost. Now, we can also use the Pythagorean theorem. And if we do that, that's a squared plus b squared equals c squared. We have 60 squared plus 80 squared equals c squared. That's 3,600 plus 6,400 equals 10,000. So c squared equals 10,000, and c is the square root of 10,000, which is 100. So we get the same answer using either method. We can use graph paper or we could use the Pythagorean theorem. As we can see from that problem, it might seem kind of surprising to you, but it works out in the physics. An airplane flying at right angles to the wind gains speed relative to the ground. In the next section, 3.3, let's take a look at components of vectors. A single vector can be replaced by two vectors in the x and y directions. These x and y vectors are called components of the original vector. This process is called resolution. So in the previous problem, we took a look at the airplane with the different velocities, the velocity of the airplane, the velocity of the wind. But we could have just taken a look at the direction we saw the airplane and its velocity from the ground and broken it into the x and y components that we started with instead. This is commonly done, say, if we wanted to figure out the velocity a swimmer was swimming or somebody canoeing in a boat across a stream that's going at a certain velocity. We would see them traveling diagonally. But if we broke it into its component vectors, we could figure out the velocity of the canoe going across the stream and the velocity of the stream separately. We're going to take a look at some more of these problems in class. For this last example, we are going to say that from the ground, an airplane is observed flying 106 kilometers per hour to the northeast. And I want to resolve this vector into its x and y components because I know that this plane is traveling east, but it's being caught by a northern crosswind. So let's see what its component vectors would be. So we do the opposite of what we were doing before. Instead of having the x and y components and completing the parallelogram and drawing the resultant in, now we have the resultant and we want to draw a parallelogram around it. So our parallelogram will look like this. I'll draw my y component here. Maybe I wanted to get away from pink, but pink seems to show up the best. So I'll go back to pink. So here's my y component. Here is my x component. And if I complete my parallelogram with dashed lines, I should probably use a ruler. This is what it looks like. And so I can see if each of my squares still stands for 20 kilometers per hour, I can see that I have 20, 40, 60, 80, 100 kilometers per hour on the y-axis, which is what the plane is traveling, and the crosswind is 20, or excuse me, 40, because they're each worth 2, 40 kilometers per hour. So it's just the opposite process. And then if I were to use Pythagorean's theorem to plug these numbers in, I would actually find that I am pretty close with this. I think when I use Pythagorean's theorem, it comes out to 108 kilometers per hour. So using this graphing method is actually really close if I check my answer with Pythagorean's theorem. So our objectives were to distinguish between a vector quantity and a scalar quantity and give examples of each, which we did, to draw vector diagrams for velocities, use the parallelogram method to find the resultant of two vectors that have different directions, and given a vector, resolve it into horizontal and vertical components. Knowing how to do this is going to help us when we talk about projectile motion in the next sections, in the next video.